Welcome to Mastering Analog. Today we will be discussing problem number 2.1 from chapter 2 of Design of Analog CMOS Integrated Circuits by Behzad Razavi. So in this problem we are given W by L as 50 over 0.5 and we are asked to plot the drain current versus VGS of an NFET and PFET, as the VGS varies from 0 to 3 volts and they have asked us to assume VDS as 3 volts. These are the specs of NMOS and PMOS models and we'll be using them as we go through the calculations. So again, we are given that W by L is 50 over 0.5, VDS is 3 volts and VGS varies from 0 to 3 volts, and we need to plot ID versus VGS. So if you look at the basic ID versus VGS curve, this is how it looks like. When VGS is less than VTH, there is no current in the device as the device is turned off, and hence we have no current here. And as VGS becomes greater than VTH, then the current starts to increase in an exponential way. Just as a side note here, so this is for a constant VDS, alright, and if you increase the VDS, then the current will look something like this. So essentially what it means is, for a given VGS, the higher VDS will have a higher current than the lower VDS. Alright, now we are interested to find what this value of current is. Alright, so this is how it looks like, the problem statement. You have an NMOS, your VDD is 3 volts and VGS varies from 0 to 3 volts, and you want to find the current ID. Alright, and as I mentioned, when VGS is less than VTH, the device is off, there is no current in the device. But when VGS is greater than VTH and VDS is greater than VGS minus VTH, then the device is in saturation. Alright, so these are the two conditions for the device to be in saturation. So therefore, when VGS is 3 volts, VDS is also 3 volts, so this implies saturation. So an easy way to know if a device is in saturation or not is, you need to look at the gate to drain voltage. Alright, so if the gate to drain voltage of an NMOS is less than one threshold voltage, then the device is in saturation. Alright, if it is greater, if VGD is greater than one threshold, then it is in triode region. Alright, so now VGS is also 3 volts and VDS is also 3 volts, so VGD is essentially 0 volts and it is less than one threshold voltage, which is VTH for NMOS, which is 0.7 volts. So therefore it is in saturation, and in saturation the current equation is given as ID is equals to 1 by 2 mu n Cox W by L VGS minus VTH the whole square times 1 plus lambda VDS, if you want to include channel length modulation as well. Now this is a golden equation. It's a standard current equation for a device in saturation. Alright, now you need to know one more thing here as to how do you calculate the Cox here. Alright, so I have a quick trick to calculate the Cox. So Cox for a Tox of 1 nanometer is given as 35 over 1 femtofarad per micrometer square, which is essentially 35 femtofarad per micrometer square. Now as the thickness increases, alright, so you just increase the denominator here. Alright, it was 1, now it's 5. So Cox for Tox equals to 5 nanometer is 35 over 5 femtofarad per micrometer square, which is 7 femtofarad per micrometer square. Similarly, if Tox is 7 nanometer, then Cox would be 35 over 7, which is 5 femtofarad per micrometer square. Alright, so that's how you calculate Cox based off of Tox. Okay, and one more thing, the L in this equation here is nothing but L effective. So there are two L's, something called as L effective and something called as L drawn. If you look at the cross section of an NMOS, then it's built on a P sub, and then you have two N plus regions, namely source and drain. Now, when you draw it, when the designer draws it, then this is basically L drawn, the length of the channel actually. But when the chip goes into fabrication, then these N plus regions encroach into the channel and effectively reduce the length of the channel, and that's how we define L effective. And this is the encroachment area on the source side, and this is the encroachment area on the drain side. And if we call it to be LD, then L effective is essentially L drawn minus 2 times LD. Alright, so let's go back into the equation, plug in all the values and see how much ID do we get. So again, we have ID equals to half mu n Cox W over L effective, right, VGS minus VTH the whole square times 1 plus lambda VDS. Now, it's confusing at times, but you need to be very careful with the units. Alright, so I'll walk through this equation step by step and how I calculate the ID. Alright, so we want to calculate ID at VGS equals to 3 volts. Alright, so you have half mu n for NMOS is 350, and the units are 350 centimeters square per volt second. Alright, so that's what I have here. And W over L effective. Okay, so sorry, you have mu n, then Cox. Alright, so this is just mu n, and Cox, the way we calculate Cox again is 35 over the Tox, and Tox for NMOS is 9 nanometer. Alright, so you don't write 9 nanometer here again. Alright, it's just 35 over 9 femtofarad per micrometer square. Alright, then 50 over, it's W over L effective. We were given it's 50 over 0.5, but L effective is basically, this is L drawn, 0.5 is L drawn, minus 2 times, we are given LD as 0.08 micrometers. Alright, so 0.5 minus 2 times 0.08, that is L effective. Okay, then VGS is 3 volts, VTH is given as 0.7 volts. Alright, so 3 minus 0.7 the whole square times 1 plus lambda is given as 0.1, VDS is again 3 volts. Okay, now I simplify the units and bring it to one standard units. So half 350, I convert centimeter square to meter square. So 1 centimeter is 10 to the power minus 2 meters. So since we have a square, we get 10 to the power minus 4 meter square plus volt second. Okay, then 35 over 9 is 3.8. I convert femtofarad per micrometer square to farad per meter square so that these cancel. Alright, the meter square. So femtofarad is 10 to the power minus 15, and micrometer is 10 to the power minus 6 meters, but since we have a square, it's 10 to the power minus 12 meter square. And this comes out to be 50 over 0.34, then 2.3 square times 1.3, which eventually gives us ID of 67.2 milliamps. Alright, and this is what the curve looks like. So you have, again, VGS is less than VTH, there is no current. VGS greater than VTH, the current follows this trace, and for VGS equals to 3 volts, we have a current of 67.2 milliamps. Now this is for a constant VDS equals to 3 volts. Similarly for PFET, we have this situation. You have a mod VGS of, it goes from 0 to 3 volts, and then you need to find ID at VDS equals to 3 volts, mod VDS. So with the PMOS, right, you need to be very mindful of the mod here. So again, when mod VGS is less than mod VTH, device is off, there is no current, ID equals to 0. And the same equations for saturation hold for PFET2. So if mod VGS is greater than mod VTH, mod VDS is greater than mod VGS minus mod VTH, then the device is in saturation. Again, if you look at gate to drain voltage, if VGD of the FET is less than one threshold voltage, which is VTH, then the device is in saturation. Here VGS is 3 volts and VDS is 3 volts. So gate to drain voltage is essentially 0 volts, which is less than one threshold voltage for the PFET, which is 0.8 volts. And therefore it's in saturation. And we have the standard golden equation for current in saturation is half its mu P here, COX W over L effective mod VGS minus VTH the whole square plus 1 times 1 plus lambda VDS if you want to include the channel length modulation. Again, being mindful of the units here, half mu P is 100 centimeter square per volt second, and the COX is again 35 over 9. 9 is the TOX for PFET, femtofarad per micrometer square. W over L effective. L effective is 0.5 minus 2 times LD, and LD for PFET is 0.09 micrometers. Alright. Then 3 minus 0.8 the whole square times 1 plus lambda is 0.2 for PFET, and VDS is 3 volts. Now again, converting the units to standard units. So centimeter square per volt second becomes 10 to the power minus 4. Femtofarad per micrometer square becomes 10 to the power minus 15 over 10 to the power minus 12 farad per meter square. This comes out to be 50 over 0.32. Then we have 2.2 square times 1.6. Alright. That eventually gives us an ID of 23 milliamps. So when mod VGS is 3 volts, we have an ID of 23 milliamps. And this is for a constant VDS of 3 volts. So this is the solution for problem number 2.1. In the next video, we'll discuss the solution to problem number 2.2. Thank you.